Now we're going to talk about how we can use the vertex form of a quadratic function to solve some applications problem. And in particular, when we have a type of word problem, how do we interpret it and translate into a mathematical expression with the vertex form? So in this example 1, take a minute to read the question first on your own before you continue the video. Whenever you're ready, in this question, we know that a golf ball is hit off on a rooftop 50 feet above the ground, and we also know the golf ball reached a maximum height of 150 feet when it's 300 feet away from where it was hit. And using this information, we want to determine the vertex form of the function. And to write the vertex form of the function, again, we want to talk about how we can describe things using the form first. And here we have the height of the golf ball and the horizontal distance of the golf ball. So I'm going to go ahead and define the variables first. So we can let d equal to the horizontal distance from where the ball was hit. Measured in feet, since the information we're given is in feet. And we can use h to represent the height of the ball in feet. And in this case, we really have these two variables being involved, and eventually we want to use the vertex form to create a graph for the path of the ball. And because we have the horizontal distance and height, which is vertical distance, I'm just going to use a horizontal axis to represent distance and vertical axis to represent the height in this case. And they're both measured in feet. And with this information, we are going to go ahead and start with the function notation. And here we can, or the equation form, we can say h is dependent on the distance over here, or h is related to what we have for the horizontal distance. Here we can say this is equal to the standard form being a times. Normally we would use we would use x, but in this case we have the horizontal axis defined to be d, so we can just use d over here minus whatever the vertex coordinate is. I just noticed the vertex usually we use hk, so I could go ahead and change the vertical distance to be v over here. That way we have some differentiation between what we're trying to represent. And we can do d minus h squared plus k. And I left h and k being in red to indicate that that's what we want to find in terms of the vertex. And also a is going to be something we'll need to find next. But let's start from hk. hk is going to be the vertex. And the vertex in this case for the path of the ball should represent the maximum height if you're hitting a golf ball. And in this case we know it's 150, 150 being the height and 300 being the horizontal distance. So it would be 300, 150, like this. And with this information we can go ahead and plug that in. So we have a times d minus 300 squared plus k, which would be 150. And just like I almost made a mistake, really be careful with which one represents a horizontal distance, which one represents a vertical distance, and that's going to determine our x and y coordinates, in this case d and v coordinates over here. And once we have this form, we want to go ahead and find out what the value a is equal to. And that comes down to the other point we were given, that when it was first hit off, it is 50 feet above the ground. And when that information is given, that tells me when it was first hit, there's no horizontal movement at all in terms of distance. So the horizontal distance was at 0 feet away from where it was hit. But now we already know that it was hit 50 feet above the ground. So it started at 50 feet in height over here. So that's a point we want to use. And we know when v was equal to 50, that d is equal to 0 in this case. So we would have 50 is equal to a times 0 minus 300 squared plus 150 in this case. And once we have this form, we can go ahead and simplify to solve for a. And therefore we get 50 is equal to a times negative 300 squared becomes 90,000 plus 150. And then once we have this form, we can subtract 150 on both sides to get negative 100 equals 90,000 a. Now to find a, we can go ahead and divide 90,000 on both sides. Therefore, we get a is equal to negative 1 over 900 over here with a cancellation. And once we find this out, we can go ahead and plug everything in to write the vertex form. So we can say v is equal to negative 1 over 900 times d minus 300 squared plus 150. And that's going to be the vertex form we can use in order to graph. And to create a graph, we definitely want to use the key points that we were given. The 0, 50 is where we started off, and we also have 150 and 300 feet over here being the maximum value. And to graph it, we still want to use a few other points just so we can make sure that we get the important information on over here. Now to find the key points, I moved things around a little bit so we can make room for fitting more information into the screen. And the first point we are going to have is 0, 50, then we have the vertex. So we can use this information to help us find what's going to be the mirror image of the y-intercept over here. So when we have 0, 50, this is going to be the starting point for the path which shows the y-intercept. If we want to find the mirror image of the y-intercept, that can be one point that we can use as a special point. And we know for the mirror image of the y-intercept, it would have the same height as a y-intercept, meaning the height would still be 50. And in terms of the horizontal distance, it should be on the other side of the axis of symmetry. And from our vertex, we know that our axis of symmetry is x equals 300. So to find the mirror image, we're just going to double that 300 to find this is going to be 600, 50. And that's going to be a point we'll want to use later on to help us graph the path as well. And then another point we can find is the horizontal intercept. And to find the horizontal intercept, we still want to go ahead and find when the y is equal to 0, or the height in this case is going to be equal to 0. So when I say the y-intercept, in this case it would really be the v-intercept, or the vertical axis, vertical intercept. And now if we want to find the horizontal intercept, which we represented with d over here, we want to go ahead and set the entire function equal to 0 over here. So if we want to go ahead and find horizontal intercept, we would get that 0 is equal to negative 1 over 900 times d minus 300 squared plus 150. And to solve that, we are essentially going to again try to move things around so we can have a perfect square by itself, and then we can use a square root method for this. So to isolate things, we want to subtract 150 on both sides first. We get negative 150 is equal to negative 1 over 900 times d minus 300 squared. Once we have this form, we can go ahead and multiply negative 900 on both sides. So if I multiply negative 900 on both sides, I can get rid of the fraction on the right hand side and multiplying this negative 900 over here. I'm going to create a barrier between the information. And in this case, once we multiply this out, we should get 135 with 3 zeros, 135,000. And with a cancellation on the right hand side, we would get this is equal to d minus 300 squared. Now once we have this form, we can go ahead and use the square root method. And in this case, once we take the square root, remember we're looking for the horizontal distance. So it doesn't make sense for the distance to be negative. In this case, we would only want to take the positive answer for our result. And therefore, that would give us d minus 300 on the right hand side. And on the left hand side, we can simplify things a little bit before we write out the final answer. In particular, for square root of 135,000, this is equal to square root of, you can say 100 times 10 to give us a 1,000. So this leads to some factorization we might want to work on the side. So if we have 135,000, in order to simplify the radical, the goal for us is to find as many perfect square factors as possible. And we know this is equal to 135 times 1,000. And 135 itself is equal to 15 times 9. And 15 again becomes this number that doesn't have perfect square factors, but we can factor it further to be 3 times 5. And 9 can be factored out to be 3 and 3. We know 9 is a perfect square factor. And for 1,000, we can write 110. 100 again becomes a perfect square factor over here. 10 can be factored further to be 5 and 2. In this case. So I'm going to leave the 900 as is in terms of factor because I know I can simplify them easily once I take the square root. And for the rest of the factor, it's 3 times 5 times 5 times 2. So this tells me 135,000 is equal to 9, which is 3 squared, times 100, which is 10 squared, times 3 again, times 2, and lastly times the 5 squared because we have 2 factors of 5 in the prime factorization. And now that makes it a lot easier to take apart once we take the square root. So if we kind of organize things a little bit, I'm going to put the perfect squares first. So we have 3 squared times 10 squared times 5 squared, then multiply by 3 and 2 once we want to take the square root. And this is a good practice for simplifying radical in this case because our numbers are so much messier or so much larger in general. And once we take the square root, square root of 3 squared just becomes 3, square root of 10 squared becomes 10, square root of 5 squared becomes 5, and then we're left with square root of 3 times 2, which is 6, and this is equal to d minus 300. Now we can combine everything outside the radical. 3 times 10 times 5 will be 150. So we really get 150 root 6 is equal to d minus 300 over here. And in this case, we would want to find d by adding 300 on both sides. So 150 root 6 plus 300 is equal to d over here. And this is going to be our horizontal intercept for the path of the ball because we don't want to take the negative answer. If we had negative 150 root 6 plus 300, it would give us a negative value. And to help us graph this point, we will want to find approximately what this value is equal to in general. And we can pull up the calculator here, 150 times root 6. So we want to do root 6 first, then multiply out the 150, then add 300. We should get about 667 feet in distance over here, and that's going to be the horizontal intercept we can use. So we can have 667 comma 0 over here, and that tells us the ball will hit the ground when it's about 667 feet in terms of horizontal distance away from where it was initially hit in this case. And for other key points, you can pick any point of your choice to plug into the function and find out the values in this case to create more precise of a graph if you need to. And because our points need to be falling between x-coordinate or horizontal coordinate being 0 and 667, that's the only restriction really have in terms of picking the points. Here I'm going to pick the horizontal distance being 150, for example, because it's halfway between 0 and 300. It would give us some idea as to what the values are going to be. So when we have d equals 150, we would get v is equal to negative 1 over 900 over times 150 minus 300. So that's what I'm going to plug in, plus 150. And if I go ahead and simplify everything, 150 minus 300 would be negative 150, squared would be 225,000. And I'm just going to go ahead and use a calculator to simplify this thing all the way and get the result, which will give me negative 25 plus 150, so it works out nicely to be 125 feet being the height. And using this information, we can find the mirror point of this point over here when we have 150, 125 being the point, and the axis of symmetry to be 300. So if this is x equals 300 and we had 150, 125 over here, that distance, if it's reflected to the other side, will be over here. It would have the same height, being 125. And the distance between 150 and 300 is 150. So if we add 150 to 300, it will be 450. And we get 450, 125 being the point as well. So using all these points, I'm going to go ahead and scale my axes over here. And I want to make sure I can fit anywhere between 0 and 667 on the horizontal direction. And on the vertical direction, I need to go up to 150. So I'm going to take a minute to scale that first. And here's how I scaled things on the horizontal direction and vertical direction. Remember, we don't need negative values, so I just start from 0. And on the horizontal direction, because I need to go all the way to 667, I chose to just let every 3 boxes be 150. So that's the scale I used. And on the vertical direction, we have a bit more room. We just need to go up to 150 feet. So I just let every box essentially be 10. And using this information, if we want to put all the points on, we have 0, 50 being the y-intercept, and then 300, 150 being the vertex over here. And then we found the mirror point for y-intercept is 650. It's over here. And for the x-intercept, 667, 0. So if I use every 3 boxes being 150, that means every box is about 50. So it's just a little above this over here. And then we have the 2 points we chose randomly, 150, 125. And 125 would be right in between 100 and 150. And lastly, 450, 125. So 450 is right here between 300 and 600. So now I have 6 points that we can use to go ahead and connect to create the path of the ball. And because we have the result regarding the horizontal distance and vertical distance, this should be exactly the path of the ball throughout this process. And moreover, we can conclude and answer the question that the ball would hit the ground when it has traveled 667 feet. Horizontally. And that concludes this question.